Hello everyone, welcome to the last minute revision tips video for Unit 2, exam tomorrow. So there are three sections in Unit 2. Those are electricity, waves and nature of light. Let's first focus on electricity. So I have mixed two concepts here. One is series parallel ideas and the other one would be transport equation. Both of them are really important for your exam. So we have two wires here, one thicker than the other. Thicker means it has a larger cross-sectional area, and since they are connected in series, the first diagram of course, the current is the same through both. Since Z has a greater cross-sectional area, according to I equals to NAV, that is the transport equation, I remaining same, if A is greater, drip velocity will be smaller. And since W has a smaller cross-sectional area, its resistance is greater, and this is from resistance equals rho L by A. So resistance and cross-sectional area are inversely proportional. And you have to also recall how voltage is shared in a series circuit. So total voltage is shared according to the ratio of the resistance. The higher the resistance, the greater the voltage. And since W has a higher resistance, the PD across it will be greater as well. Now moving on to the two wires connected in parallel. PD is the same across both. Why? Because in parallel circuit, the voltage remains the same. Z has a larger cross-sectional area, so resistance is smaller. Since V equals IR, voltage remaining same, since Z has a smaller resistance, current through it will be greater. And if it has twice the diameter, it will have twice the area as well. So if you recall the transport equation, I equals NAVE, twice the diameter means twice the cross-sectional area, and if resistance is halved, current will be doubled as well. And resistance, if it decreases by 4 times, current will increase by 4 times. So if both cross-sectional area and current increase by the same amount, the drip velocity will remain the same. Next, we have to look at behavior of semiconductors. This is a very common question and a frequently asked question. So first, look at a thermistor. As temperature increases, more electrons move into the conduction band from the valence band. So now there are more number of electrons per unit volume. So this increases the charge carrier density. As as N increases, the I also increases. So according to V equals to IR, since current increases, the resistance decreases. So this is how an increase in temperature decreases the resistance of a thermistor. Now let's look at an LDR. As light intensity increases, more electrons move into the conduction band. It's very similar. If you look at the 2 points, it's very similar to a thermistor as well. So now the number of conduction electrons increases, so current increases according to I equals to NAVE. And exactly the same format, the only difference would be in thermistor the trigger is temperature, and in LDR the trigger is light intensity. Other than that, it's the carbon copy. Now you have to recall the behavior of filament bulb. As current flows through the filament, the temperature increases. Amplitude of vibration of the lattice ions increases. So this causes increase in collisions with electrons and lattice ions. And this would decrease the drift velocity. And according to I equals NAVE, if drip velocity decreases, current also decreases. And according to V equals IR, V remaining same, if current decreases, the resistance increases. Now let's talk about internal resistance. So this is the circuit we use to study internal resistance of a battery. You can clearly see we have a variable resistor here, and when the resistance is varied, the current as well as the voltage, the PD, terminal PD, will also vary. So with multiple values of current and potential difference, you can plot a graph. This is what the graph would look like. And some features of the graph are very important. The y-intercept gives the EMF of the battery. The negative of the gradient of the graph gives the internal resistance. Now, if a voltmeter is connected directly across the battery, it measures the EMF. Why? Because the voltmeter has a very high resistance, no current flows to the circuit. Since no current flows, there is no voltage lost across the internal resistance. So no lost volt. In other words, there is no potential difference across the internal resistance. Now, if you connect another identical cell in series with this cell, the EMF and the internal resistance will both be doubled. In electricity, whenever you come across a resistivity question, it's connected with dimensions of the material. Always recall the equation, resistance equals rho L by A. Just plug in the values and you'll get your answer. In series parallel calculations, it's very important to recall the equation for total resistance in series. So in series, the total resistance is given by just the sum of the resistances. But when it comes to parallel, the equation is a bit different. It's 1 by RT equals 1 by R1 plus 1 by R2. This is a combination circuit. So these two are in parallel, and if you have to calculate the total resistance of this circuit, what you'll have to do is calculate the individual calculate the total resistance in the parallel branch, and these two are in series with this one. So you find out the total resistance in parallel and then add it with the resistance of this resistor. Next, we move on to waves. One of the very common concepts would be calculating refractive index. Always remember, all angles must always be measured from the normal. So you see two values here, 32 and 50. You cannot do any calculations with any of these two values. The very first thing you'll have to do is draw a normal here. So you find out this angle with the normal and this angle with the normal, and then do calculations for refractive index using these two angles from the normal. And previously, the equation was n equals to sine A by sine R. It's not appreciated anymore. Now the equation is n1 sine theta 1 equals to n2 sine theta 2. So n1 would be the, over here, refractive index in air, and sine theta would be the angle in air, equals to n2 would be the refractive index of glass, and sine theta 2 would be the angle in glass. So when it comes to air, the refractive index of air is 1. So you plug in the values and you calculate refractive index of glass. Now, very, very, very important, polarization. This diagram will help you a lot to visualize how to distinguish the whole concept of polarization in terms of plane and in terms of direction. Actually, sorry, this will be in terms of direction, not plane. Now, a common question is, what is the difference between polarized light and unpolarized light? So in polarized light, oscillations are in multiple planes. In unpolarized light, oscillations are in multiple planes. In polarized light, oscillations are only in one plane. And when you are answering in terms of plane, the third point is which includes direction of wave travel. What do you mean by which? Which as in the plane includes direction of wave travel. So this is your approach when you are answering in terms of plane, and when you are answering in terms of direction, answer is unpolarized light has oscillations in multiple directions. Polarized light has oscillations in only one direction. The third point is which is perpendicular to the direction of wave travel. Look at the two differences in terms of plane. When you are writing in terms of plane, you write which includes, and when you are writing in terms of direction, you use the term perpendicular. So the image here, the diagram here will help you a lot to distinguish how do you write in terms of plane and how do you write in terms of direction. You can clearly see this from the diagram. And then a common question is how to demonstrate whether light is plane polarized or unpolarized. What you have to do is you direct light through a polarizing filter. If the light is unpolarized, there will be no change in intensity. And guess what? If the light is polarized, the intensity will change after every 90-degree rotation. The intensity will change between maximum and minimum after every 90-degree rotation, if and only if light is plane polarized. And I repeat, if light is unpolarized, once you pass light through a polarizing filter and rotate it, there will be no change in intensity due to the rotation, of course. Next, move on to pulse echo technique. So I have two scenarios here, both from the question paper, both from somewhat recent question papers. One is of an unborn child, the other one is using ultrasound to detect cracks in metals. The answer is regardless the same. Ultrasound is reflected from the boundaries. Why is there a reflection? Because there is a change in density. Now the time taken between the pulse being sent and received is measured, speed of ultrasound is known, and you use the equation speed equals to distance by time to calculate the distance. But wait, the time that you are measuring here is the total time. So the distance you'll get is the total distance, but you don't want the total distance that the pulse travels. You just want this distance. So you have to divide the distance by 2. Next, we have superposition and interference. When you look at these two setups, again, both from the question paper, the first scenario says, explain why both loudspeakers are connected to the same signal generator. And the second question says, explain why it is not possible to create a consistent interference pattern on the screen using this arrangement. Both questions will have the same answer. To get a stable interference pattern, the waves must be coherent. And what does coherent mean? Coherent waves have the same frequency and a constant phase relationship. This is the 2-mark question. Then you have superposition and interference. Again, one of the most common questions. So waves passing through these slits undergo diffraction and they superpose at point X as well as point A. There is no path difference, or the waves are in phase. And when two waves are in phase, they undergo constructive interference at both X and A. And when you move away from X, the phase difference changes. And at a position where the waves are in antiphase, the waves undergo destructive interference. These are the 6 most common points. Please have them memorized for your exam tomorrow. Then you have standing waves in string instruments. The first one is a harp, the second one is a violin, and next year might be a question, or even your year, you might get a question using a guitar. So how is a standing wave formed on a string? So it's actually a 3-mark question, and I have written the 3 points in 3 different colors. Wave on the string is reflected, point 1. Where do they get reflected? At the end, and superposition takes place. These are your 3 points. And when it comes to standing waves in string instruments, the equation that is most useful is V equals to root over T by mu, where V is the speed of the wave that is traveling. T is the tension in the string, and mu is mass per unit length. Mass per unit length. Now in a string instrument, if it is oscillating with the frequency f0, which is the fundamental frequency, like this, there will be a node at each end and an antinode in the middle. And if the same string were oscillating at twice f0, this is what it would look like. There will be two loops, and if you look at the shape, this doesn't look like one wavelength, does it? So the length of the string is equal to half a wavelength, but this looks like a complete wavelength. So when it is oscillating at twice f0, the length is equal to lambda. So in recent years, most common questions are with standing waves in string instruments, but you have wind instruments in your exam as well. So we have to look at standing waves in wind instruments. So there are two types of wind instruments. One is open-ended, where both ends are open, and you have closed-ended, where one of the ends is closed. So always remember, there is always a node at the open end and an antinode. Sorry, there is always an antinode at the open end and always a node at the closed end. So in open-ended ones, there is no node at the open ends. Both ends will have an antinode. And when it comes to closed-ended instruments, always remember, even when you say closed end, you mean one of the ends is closed. There is always an antinode at the open end and a node at the closed end. And you can work out from here what will be the length equal to, what will be the wavelength compared to the length of the wind instrument. I can give you one example. When you look at this doesn't look like one complete wave. If you do this, then you get one complete wave, but this looks like half of a wavelength. So length is equal to lambda by 2. And the moment you double the frequency, twice f0, this pattern doubles. So this time the length is equal to wavelength. And once you triple the frequency, this pattern is repeated 3 times over here. And when it comes to closed-ended instruments, one very important point to address is in open-ended ones, you get standing waves at f0, twice f0, thrice f0. But when it comes to closed-ended ones, you only get standing waves at f0, thrice f0, and 5f0 at odd multiples of the fundamental frequency. Why not at twice f0? Because if a standing wave were to be formed at twice f0, over here would have been a node, and we all know in wind instruments you cannot have nodes at the open ends. That's why. Next up, we have diffraction grating. Every time you come across a question associated with diffraction grating, just recall the equation n lambda equals d sine theta, where n is the order of maximum, and in this specific question, since we are dealing with the first maximum, the value of n would be 1, and this is the theta which we always consider from the central maximum. D is the slit spacing, or in mathematical terms it's 1 by lines per meter, and lambda is the wavelength of the light from the light source. So a lot of people have confusions with this D. What is this D? So this diagram will help you a lot to identify what this D is. So let's say you have a diffraction grating with many slits, and the distance between two slits is your D, the slit separation or slit spacing. Next, you have calculations involving light intensity. So there are two separate scenarios you have to address. One would be light being incident perpendicularly on a surface. The other one is light incident radially from a point source. First, look at the first section. So when you have light perpendicular on a surface, the equation is intensity equals power. Of course, always remember, in these questions the power has to be in the form of light, and if it is incident perpendicular on a surface, the area is the area of the panel always. So a lot of times if it's a solar panel, uh, you have light falling on the solar panel and you get an output. So can you guess what an output form is from a solar panel? It's always in the form of electrical energy, and the power output that you get is electrical power. So this is where the concept of efficiency comes in. So let's say if this is 15% efficient, 15% efficient at converting this light energy into electrical energy. So from this equation you calculate the power in the form of light, and of this power 15% of this light is being transferred to electrical power. And this is your output power from a solar panel. And then you have radially from a point source. So in these scenarios you can clearly see that the light bulb emits light radially, so it emits light in the form of spheres, and the area of a sphere is 4 pi d square. So let's say you are at a distance d from the light source. So over here the intensity would be power. Of course, again, in intensity questions power is always in the form of light divided by 4 pi d square. Next we have nature of light or nature of particles. There are three sections under this. So one would be photoelectric effect, second would be energy level transitions, and third one would be wave nature of electrons. Let's look at the photoelectric effect. A lot of times students mix up photoelectric effect with energy level transitions. Make sure you never do that. First look at photoelectric effect. What happens in photoelectric effect is light is incident on a metal surface, and from the energy of the light the electrons are ejected, and the most important equation in calculations would be energy of the photons is equal to work function plus kinetic energy of the electrons. And energy of the photons can be calculated using two ways. One is in terms of frequency, which is hf. The other one would be in terms of wavelength, which is hc by lambda. And phi is the work function, and half mv square is the kinetic energy of the electrons. So always remember, in photoelectric effect you are always considering electrons being ejected from a metal surface, and photoelectric effect demonstrates the particle nature of light. Before this we used to consider only the wave nature of light, but photoelectric effect tells you the particle nature of light. So these are the points. There is a minimum or threshold frequency for electron release. Electrons are released instantaneously. Changing the intensity does not affect the kinetic energy or speed of the electron. The energy of a photon increases as frequency increases. Photon energy has to be greater than the work function. Each photon only interacts with one electron. So this is what you use to investigate photoelectric effect. When you change the frequency and plot a graph of kinetic energy against frequency, this is the graph that you get, and the gradient of this graph gives you the Planck's constant, and the negative of the y-intercept gives the work function. The x-intercept gives the threshold frequency. If you repeat the experiment with different metals and plot a graph on the same axis, the graphs will all be parallel to each other. Why? Because the gradient gives the Planck's constant, which is always constant. Now, we have energy level transitions. Always remember, an electron rises to a higher energy level when it absorbs a photon, and an electron drops to a lower energy level when it emits a photon. So this is the building blocks of energy level transitions and emission spectrum and absorption spectrum. So these two lines summarize literally the whole concept of emission spectrum and absorption spectrum. In either case, the energy of the emitted or absorbed photon is equal to the difference in energy levels. This is super important with calculations. So the energy of the photon is always equal to the difference in energy levels. And finally, the wave nature of electrons. Back in the day, electrons were considered to be just particles. But once we um, directed a beam of electrons at high speeds through graphite, we were really surprised by the result. We saw a diffraction pattern. Diffraction is a wave phenomenon, and the fact that electrons can exhibit diffraction tells us that it must also have wave properties. And this is a very common question, and these are your points. What can you deduce from this pattern? So electrons can exhibit wave behavior. Electrons diffract as they pass through graphite. The structure of graphite must be ordered or regular or layered. The de Broglie wavelength of the electrons is similar to the spacing of gaps between atoms, because in order for the electrons to diffract, their de Broglie wavelengths must be similar to the spacing between the atoms. And talking about de Broglie wavelength, you have to do some calculations quite frequently as well. And every time you come across de Broglie wavelength, this is the equation that you use: lambda equals h by p. Thanks for watching.